Yeah, thanks a lot, Luis, for yet another time organizing and yet another time inviting me. It's an honor, and it's also a great pleasure to see people like in real life again and see friendly faces. I have missed that a lot. It's so much better in real life. So let's keep doing that in real life. So this presentation, I will tell you about a problem that I have been working on and with over the past 6 years in the context of Actix, the company that I co-founded with 2 others. We make software for factories, for automation of the processes on the shop floor. And yeah, so it's decentralized peer-to-peer event sourcing, and I'll tell you why and what the problem is. There is an existing and implemented solution, I would say. It works quite well. People are using it. It's used in production, in real production facilities, so it's real production. I spoke about that at least last 2 editions here in 2018 and 19. So it works, but I'm sure it can be improved. So this is, I would not call it a solution yet, it's more an approach. But first, let's talk about the problem. The problem I would like to frame in this context. So Peter van Hardenberg, that's PVH for short, to get the title on the slide, will speak later today and introduce you properly to local first software, where he'll, I assume, focus on ownership and agency over data and so on. I will focus on a slightly different aspect, which is why I added this word cooperation here. So local first cooperation. There's also more about that on this website that you see the link here. The idea is I have these devices, can be anything, can be mobile phones, can be robots, can be like industrial gateways, can be whatever you want. And the idea is they need to work together in order to fulfill a common purpose that is greater than each single one could achieve. So having 2 devices is 2 times, at least 2 times as useful. Having 3 devices is, I don't know, 6 times as useful. So the value is increased by cooperation, by collaboration between these. Now, when they are in proximity, logical or physical, so they can talk to each other, the idea is of local first cooperation that this should happen locally as much as possible. So without any intermediaries, without the cloud or a message broker or what have you. The idea is to explore what happens if we let these just talk to each other and figure things out. How to implement some scenarios. And I'll show you 3 scenarios to get you in the right state of mind. The first one, I mean, I was traveling. I haven't been traveling so much for the 2 previous years. So a taxi service kind of sprang to mind when I was getting here. Imagine there's this fleet of taxis, the yellow boxes, and they are somehow meshy connected to each other. And there's a passenger here who wants to ride from home to the airport, for example. Now, wouldn't it be nice if the passenger could just say, I want a ride from A to B, and then this information circulates among the taxis, and they can place bids and tell you, okay, I can be there and pick you up in 8 minutes, and it will cost you approximately this much. And others might be interested and place bids. And then the passenger says, yeah, I want this taxi to bring me there, and then it happens. This doesn't really need central coordination, I think, right? You could also do it with a group of people, and groups of people don't run Paxos voluntarily. So it would be possible to implement that. It should be possible. Another use case that is conceptually very similar, which is one of the use cases I've been working on at Actix, is you have a machine or a machining center here, the red dot. The function of this is the main function of the factory. So you have input materials, and you do some process step like milling, cutting, or filling, or assembling, whatever, and then you have an output product. So this is the real thing that the factory does. Everything else is just decorum or overhead, but this is the thing that needs to work. Now, you need to get the input products to input material to the machine, and you need to transport the produced goods into the warehouse or to the shipping area. Now you have a fleet of different things, like you have gateways that are in gray here, or you have vehicles, autonomous ground vehicles with a robot on top that can drive to the machine, pick up the pieces and get them elsewhere. Now, it's like a taxi service, isn't it? So the machine can say, I have something produced, you need to bring it to the warehouse. And then you run an auction-like algorithm to figure out which of the vehicles is most suited to do it. You could take into account battery level, put current position, backlog of things to do, and then figure out, so they can place bids, and then you decide, and you get, hopefully, a near optimal solution. Does that make sense to you? Yeah, okay. So these are pretty similar, but we can also do very different things, I think. I see no reason why we couldn't have a social network that is just us connected. No servers, none at all. Not even as in Mastodon or Matrix, where you need these servers to, I mean, it might be federated and so on, but you still have servers. But I don't think we need servers, really. We could just run a social network purely on our phones. I think it should be possible. Do you agree? I post something, you should be able to see it, right? Okay, so now the big question is, and this is the core of the problem, we agree it should be possible, but who here has a clear picture of how you would do that? Well, Peter, of course. Right, so not many people. And this is the core question. How do we model such a problem? How do we attack it as programmers? Now, yesterday, Carlos Baquero and Nuno Preguiça, sorry, I'm stumbling. They held a very good introductory presentation yesterday in the main hall about CRDTs. And they showed us basically how they work, some of the options that are there. It was kind of an overview. I'm giving you a slightly differently focused overview here. So CRDTs are really nice for working together. Everybody can basically edit a shared document. I mean, what they presented was a set, and you can put things in, but you can make much more complicated structures, also as Nuno discussed afterwards, with multiple of these combined and so on. So everybody sees a shared copy of the data and edits it. The edits are called operations and are sent between the devices, synchronized, and if there are, so there cannot really be conflicts. If there are edits for the same thing, then they are merged in a predetermined fashion to produce a result. Now, there are different ways of choosing this result, as discussed. So the add win set or the remove win set or whatever have you. But the result is always valid in a programmer sense, and now you need to pick the right tools to assemble your data type that you need, for example, for your taxi service or for your social network. What I would like to mention is there's a distant cousin that was kind of a precursor to this, I think. Correct me if I'm wrong. It was the operational transform that was developed, I think, at Google. The sources are a bit unclear. It is basically what powers this presentation. So it powers Google Docs, Google presentations, and so on, Google Sheets. So CRDTs would be possible to model this as well. Google probably wouldn't use it because the main difference is operational transform assumes that all the operations go through a central server, while, yeah, well, it gets easier that way. Okay. Anyway, so no matter, so we heard about that a lot, but I think it's not enough. I think sometimes we want something else. And the thing is that CRDTs do not really inherently model coordination. They are coordination free. That's the whole purpose of them. So you can coordinate using CRDTs, but it needs to be on a higher level. For example, you could have a Google Doc and you write in it like in a chat. So you could run your own like human coordination process in a Google Doc. While the Google Doc would not make decisions, you would like use it basically for message passing. You could even run Paxos on it if you want, I guess. let's explore that a bit more in detail. So this conflict freedom by construction means it's not really good at coordination. What do I mean? So if I insert something in a set, and I want to know, was I the one who inserted it into the set? Because then, if I was the one who, like, there's a set of orders or of transport missions that have been taken, and I put myself in if I take the transport mission. So I want to naturally know whether I was the one who put in that value, because someone else might have put in that value, and we need to decide who takes the mission actually. Yeah, so this is atomic operations essentially. The next one. So if I had a Boolean flag, with the set, there might be some ways of figuring it out, but with the Boolean flag, you have an update operation on this CRDT saying set to true. And if 3 actors at the same time set it to true, well, the result will of course be that the merge is that the flag is now true, but nobody knows whose change it was. So all changes set it to true, and there's no distinguishing between them. So CRDTs are not really designed for answering this question inherently. You can look at the operation history to figure things out sometimes for some of the data types, but the best way of doing that, which I think I learned some things about yesterday from the experts, is that you put the metadata you need, like a timestamp for sorting who was first, in the CRDT. So you put it inside your data, and then on the application level, you can see, okay, there are actually 3, it has been added 3 times to the set with different timestamps and different actor IDs or node IDs, and I picked the earliest one as the winner, right? This means I implemented my own coordination, but it's not inside the CRDT, it's my application protocol that I put on top. Yeah, because, so, I mean, that's the purpose of CRDTs. I want to offer full availability, so I want to give all the nodes, even when they're completely disconnected, the ability to do all the things, and then just run with it. I think, so this is really useful, right? But I think I have discovered some use cases, or I have encountered some use cases, where I want something a little different, which is state machines. Who here loves state machines from computer science, right? So programmers, yeah, some love them, some don't. I found that, surprisingly, non-programmers quite naturally think in state machines. If you go to a production manager in a factory and you ask them, okay, you want me to digitalize this process, can you describe this process to me? And they draw a diagram like this, because it's graphical, it's the least work, and they know, like, it's in this state, so first it's created, and then someone's working on it, and now it's done, or there's quality inspection, and there's transitions between them, which are events that actually happen on the factory shop floor. As someone picks up the work, it's something that happened, it's an event. So I've applied this here to the taxi example. So let's say someone wants to get to the airport, so they need to schedule a ride. So the ride is the entity that we're looking at. It can be in 4 states. So first, it's empty. It only knows. It only has an ID, essentially. And then the passenger requests a ride, and this event changes the state machine. I'm neglecting all the extra information, like from A to B at that time and so on. I'm just focusing on the state changes. So requesting a ride, and then the others can place bids. So that's a transition to the same state, because nothing fundamentally changes by placing bids. But at some point, the passenger, so this is why it's in blue, has selected a taxi. Now, when the taxi has been selected, the ride should happen. So the taxi eventually arrives, picks up the passenger, you like record what happened so that you can later create an invoice and get the money, presumably. And then the person needs to confirm, yeah, I'm actually at the airport now, so taxi driver shall get his money or their money. Does this make sense? Yeah. Okay. So this is why I want state machines. these state machines do not conform to any CRDT requirements naturally. They are just state machines. People write down whatever they had. Sometimes they have shitty processes, and then they first need like Accenture to fix them for those, to fix those for them. But then, so this is what you digitalize. What we want to do now is we have a state machine. Now we want to replicate it. Solutions to that, I forgot when the Paxos paper was, but supposedly that was the first or one of the first approaches to replicating state machines. That's the purpose of Paxos. How does it work? So a state machine is in one state, does a transition, and is in a new state. So you get this string of states. It's linear. It's a sequence. There's no concurrency or anything. So the main job of Paxos is to order the transactions, to create this string of events that will then drive the state machine. And if you agree on this log, on this transaction log, on the list of changes, then you can compute the outcome. And everybody will compute the same outcome because Paxos makes sure that the events are added to the log at all sites in the same order. So this protocol tells you when everyone has agreed, which means the transaction has committed, and then you can update your state and so on. So that's pretty neat because you can just use the state machine. This is what databases should use. They don't use it in many cases for performance optimizations, but this is what people assume kind of semantically that happens in a database. So I have a certain state of my table, I check multiple rows, multiple tables, relations, I figure out what state I'm in, then I'm allowing this transition, and I'm writing updates. And this whole package is a transaction, you know, and that's put in the log. Okay, this is databases. There's two problems with that. The first one is every time you want to commit a transaction, there needs to be some sort of communication happening before it commits. You cannot commit a transaction without any communication. You can batch things, you can optimize things, but in the end, communication is crucial. You need to always talk to other nodes to form consensus. There's just no way to avoid that. You can optimize it, but it never completely goes away. So if you want to have something that is extremely fast and always commits locally immediately, then this is unfortunately not what you want. The second point is there are several theoretical results proving that it's impossible to have this working at all times, no matter your network conditions. And we all know that things can fail. Anecdotally, so from this 6-year experience, it's quite rare that a switch fails or an AP fails. It happens, but it's quite rare, compared to someone changing firewall settings. And this happens on a regular basis. So the network is not reliable for one reason or another, and that can bring down the whole system. And since I'm working with factories, they cannot tolerate that. So I want something that is more available than that. So what I want, ideally, is I want the devices to have full autonomy. I want my machine gateway or the tablet that someone has to be able to work even while disconnected from the others. And this looks a bit like this. So I have 2 devices here, and they are currently not talking, and one of them has written 5 transactions or events, or however you want to call them, and the other one has written 4 of them. Now, what we do, I mean, we have these beautiful state machines. This is like the notation. Yeah. So I start from a state 0, and then I put that into my state machine transition function, F, together with event 1, and then I get state 1, and so on. I zip through the log, and I get some state on the left and some state on the right. Now the juicy question is, how do we merge state machines? Yeah, so it happened, so this is supposedly for the same state machine, happens on 2 nodes. How do we get them together? And this is the proposed solution that we implemented at Actix. All these events have a timestamp, a logical timestamp that is consistent with causality, but it's not strictly causality tracking. We are just using a Lampert clock, if you want to look it up. If the Lampert clock is the same on both for some event, the events that every event emission increments the Lampert clock, and communication increments the Lamport clock, it ticks forward. But there can be situations where like event B2 and A2 have the same. So the nodes have an ID, which is just basically the public key of their ED25519 key pair, which is unique. So we put that in the ordering as well to break ties. And that gives us a total order. Now, if we apply this total order, we immediately see there's something funny going on here. So the state machine, let's say the merged log looks like the one in the middle. Now the state machine starts with event A1, which supposedly was valid because that worked locally on the left node. And then A2, because after A1, A2 is possible. Yeah, that's cool. But after A2, there was A3. So the state machine was in the state where A3 was legal. But now I have B1 in between, which might have changed that. Keep that in mind. So we could still run the state machine, but some of the transitions that we had locally validated might now be invalid. I mean, we can compute this. It will get a result, right? It will get a result on all nodes, and it will get the same result on all nodes, so it's eventually consistent. So it has some nice properties, but it has also some interesting properties. Focusing a bit more on that. So this is the taxi example again, and this is how people think about it, how humans linearly think about it. Now, what can happen is, so the taxis have placed bids, and then the passenger pressed the button accept this, which is the select taxi. But this may not yet have reached all the taxis, so they may continue to place bids. They may now arrive later in a state where they were not foreseen in the original protocol. Is that clear? Yeah. Okay. And similarly for the record write, so we transition from state 3 to 4, and now we get some events in state 4 that were only emittable in state 3. Yep. It's not a duplicate. So let's say we have 5 taxis. 3 of them submitted their bids before the select taxi, but the 4th might have just had a race condition. It was submitting the bid while the passenger was clicking the button, and now it's ordered afterwards. So it's not a duplicate, it's a straggler, if you will. Yeah. Right, so place bid is a straggler that arrives late in a state where it couldn't have been emitted, but it can arrive in this state due to how we merge the logs. Now, this is a nice, this is benign here, because we can just ignore bids that we didn't select, right? And the record write, yeah, we don't care really. I mean, someone might want to analyze it later. Yeah, I don't know. I would probably ignore it for this state machine for now. But there's a more interesting case. So this is taxis where there's lack of trust, and this is why I let the passenger choose the taxi, so that they are less likely to be kidnapped. But if we look at the factory case, so we have the machine in red that says, I need a robot to bring me something or pick something up. And then you have this auction going on. Now you could completely farm out the decision-making to the fleet, the logistics fleet. The robots might wait for some time period, follow some protocol, and then they decide based on the bids that they have seen from their peers, and they see, oh, it's mine. I actually know the algorithm. I can see, okay, my bid is the winning bid. So one of the robots now emits the accepted, and then runs the mission, and then the machine confirms with delivered. Now here we run into a bigger problem, because 2 robots that are currently not able to communicate might have seen different bids and might have computed, oh, I'm the winner, or oh, I am the winner. And they both emit the accepted. Now we get the accepted event. So place bid we can ignore, but accepted in state 3 is a problem, because accepted means that this robot said, I start driving now. I picked this mission. I'm moving towards the machine, right? And something happened in the physical world that we need to now correct, because there's 2 robots going to the same machine in this scenario. And this is why I cite Pat Helland here. It's 15 years old, but it's still valid. I mean, go read it. It's a blog post, I think. I hope you can still find it. He doesn't describe this scenario, but it's quite similar. So it was for, the example he used was from Amazon warehouses, I think. It's the same thing. So you need to recognize that a mistake has been made, and you need to fix it. With these robots, it's obvious. I mean, one of them. So once they start communicating again, there's one that will see the accepted as a transition from 2 to 3, and that's the winner. And we will see one that sees it in state 3 and that knows, oh, I picked this, but I retroactively lost the bid, so I need to abort, and that's where the aborted event comes from. So this needs to be recorded as well. Okay, does this make sense? So people are programming like this based on what we have given them in factories, and it's working. So it has some challenges initially learning it, but it is very workable, and it produces a very robust result. So what I can tell you is this 100% availability is real. So as long as your device has power, you can operate. Sometimes you need to communicate as part of the process, and that doesn't work when you don't have network. So that's clear. But regarding the part that we provide, we strive for 100% availability, so that people are not limited by the computational model that we give them. And this is quite cool. We've seen this in action, and people have survived all sorts of outages without any downtime. So that's very promising, I must say. And the other thing is, even though there was some bashing yesterday in the keynote, so if you look at these diagrams, people draw them naturally. They give these names, like of the events and the states. These are non-programmers who talk to programmers. This is the idea of domain-driven design. I mean, you can make it a cult and then abuse it, but the core is that we get meaningful events. And that is very, very useful. And you can do event sourcing with them. So here we store the events and we compute the state from them. That's event sourcing. But what event sourcing also allows is a second look. So with a different pair of glasses. So I want to take a little detour here. Event sourcing means we have this log, and this was what drove the process. So this is like a taxi ride that actually happened. But now we might be interested just in some statistics on which routes were taken, or which routes were taken during what time of day, and so on. And so we are only interested in a subset of events. And we interpret them differently. We don't drive the same state machine. We might drive different state machines to figure out what happened, or we might just do statistics on this. And that is possible because the events have semantic meaning. We know how to interpret this event for a different purpose. This is much harder with CRDTs, with these operations or delta states, because they are very much tied to the data that you're modeling, and it's not so easy to figure out, so to lift a semantically meaningful representation from that and take a second look. So currently, I will not show you code because that's not the point here. There's an XX SDK and a library called Pond, in which currently our customers are writing code, are describing these state machines. It's basically these on-event functions taking a state, an event, and producing a new state. This is written in TypeScript because it's ubiquitous, it's easily available. We didn't have to create any language tooling. So, I mean, it's the smart thing to do, even though in factories, basically nobody used TypeScript before. But yeah, it works. So people are interested in learning that for this purpose, and they produced good results with it. But it's too verbose, right? I wouldn't want to show it on the slide because it's just too much to describe the taxi example, for example. I would speak a lot about that. I want to take another detour, a few slides detour. How am I doing for time? Yeah, so everybody's using the same state machine, and everybody eventually, so at that point in the log, will be in state 3 and will see that this second one actually lost the bid. Yeah, it would pick the next mission. Right, so the robot, I need to repeat it because you don't have a microphone. So the robot later realizes that it picked up a mission that someone else had more rights to and needs to abort and stop it. Stop driving and pick the next mission. In a factory, that's the right choice because, as I told you, the machine is the core. The machine is what you need to keep running at all costs. And having that like duplicate robot mission thing from time to time hurts a lot less than losing a transport mission, because then the machine stops. Okay. So wouldn't it be nice if we didn't have to write a new TypeScript program to take the second look at these data? So this is also one question that I have in mind. I'm using that heavily, right? So, for example, if you have a database behind powering your app, and you run it in production and everything's fine and so on, but something goes wrong, well, I mean, you always then look into the database, I assume, at least I do, look at the tables, do some queries, figure something out. I have a query language to talk to the storage backend. And that is very valuable for debugging, but it's also valuable for adding new features and looking at, okay, I want to add this thing, this functionality, how does it fit? I can design my queries by just trying them out. That's totally cool. I mean, this is superpowers. And I would like to have them for these events as well. Unfortunately, so SQL is very old, proven, mature, everything. So it would be totally awesome to use it. But unfortunately, and I mean, this might be a bit controversial, but what is not controversial is that SQL is designed for relations, for exploiting relations. So it gives you these joins and so on to work with relations. So you have your database tables, and you can like put them together in new and interesting ways. But that's the thing. It's like sets that you construct. That's SQL, and it's been made for working with the tables that are in the database. Now, what we are looking at here is not tables in a database. What we are looking at here is the transaction log. So the analog would be, you would take SQL to analyze the write-ahead log of your database. Who would want to do that? Okay, yeah, you do that because you're probably forced to, but you can, right? I mean, SQL is Turing complete. You can have recursive evaluation and everything. So you can write any program in SQL if you want, but that doesn't make it optimal for all the programs. So it's optimized for tables and not for transaction logs. These transaction logs contain gibberish. They contain unstructured data in just one sequence, and that it doesn't have relations and stuff. So yes, you can, but should you really? So this is why, I mean, a startup shouldn't, there's some things a startup should never do. You should never create a database. Accidentally we have. You should never create a language, and I'm proposing that we do. So yeah, I'm not sure I'm the smartest commercial guy, but I really love technology. So here it goes. This is a sketch. This is something I'm working on. It's in development. It's in the design phase. It's a language focused on analyzing the event logs that we have collected. I'm using it to debug customer issues, and it's helping me greatly. So at least one happy customer for this language. And some others are showing interest. So it's not completely off. So the most simple thing that doesn't show anything special yet is this setup here. So we have one of those taxi rides. Now the data are stored in ActX with tags. So you have events, and every event can have any number of tags, which are just strings. You're free to use whatever you want, but the common pattern is to use to tag entities. You can add other tags, but use it to demarcate entities. So a ride is tagged with the tag ride and with the tag ride : and then the unique ID of that ride. So from generates a stream of all events that have the tag for this ride. Filter, as the name suggests, takes out those that don't match. So this one evaluates, so underscore is the current event. So if it has a property called type, so it's a JSON-like, we use CBOR actually, it's a JSON-like data structure. So if it has a property called type with the value selected, then it stays in, otherwise disregard. And select is a map operation. Yeah? It's like the select in SQL. So here we construct, from each event we construct an object with 3 properties. We take the driver out from the event, the customer, and then you see here it's some dummy calculation. So you can do calculations here. So this is the simple structure. Clear so far? So this I could easily do this with SQL, but this should could possibly motivate what I'm after. So let's say the job is for each driver to get statistics of how long the rides were that they completed or that they accepted. You could do this with recursive queries in a table, or you could set up tables and relations and do that. But with all that, I want this to be ad hoc. I want this to be quick. So this is how you would do it with AQL. So you select from rides, so all the rides, and I assume that you tagged the events that create a ride. So the request with ride created, because indexing is based on tags, and this makes it fast. And then you might filter, so everything from this week. Yeah? So the time of the event is greater than the timestamp from Monday morning, midnight. So for all events that match this, we take the time of the event, that's called start, and then maybe duration, that's a subquery. So we have an event that started a ride. It has an ID property. I can compose the tag, so ride : and then this underscore ID thing, to get all the events for that ride. And I'm only interested in the last one, so I use the aggregate combinator, and the last stands for give me the last, evaluate what's between the parents, and if that works, give me that for the last event where it works. So here we take the time of that event minus the start, which should be the duration of the activity on the ride. Now, this subquery can yield 0, 1, 1,000 events. So it gives back an array. And this is, so maybe duration is an array, so we take element number 0. If it doesn't have an element number 0, it immediately, it filters out it stops here, yeah, it doesn't go further. So let's say we have an element 0, it means there was actually a last event. Then we do the same thing to get the driver. And then in the last step, we aggregate per driver. I mean, I'm experimenting with the syntax here. So it's a dynamically constructed object where the driver determines the bucket on the right-hand side. So in this expression, only things go for that driver. So the durations are summed, and for each duration that I put in, I count a counter up. So I sum 1, and then dividing 1 by the other is the average, right? Does that make some sense? Does it look somewhat intelligible? I haven't shown that to so many people yet. So yeah, come to me with any criticism that you have in mind. So yeah, so this allows you to query event streams in a more complex fashion without having to set up some temporary tables or do common table expressions or whatever have you. You could do it in SQL, but I wouldn't want to, because this is much less work, because it's targeted. You cannot yet try this out on the released Actix binaries because it has some unreleased features. Ask me if you want to experiment, I can give you a build. Anyway, so that was the detour. Back to eventually consistent state machine replication. So we saw the benefits, 100% availability and so on. There are some downsides, but the future plans are meant to mitigate some of those. And there's some really interesting research ongoing with some in the context also of EU projects. So the EU is also good for some things, actually, bringing me together with the researchers. That's cool. What we're working on is, for example, a formal model for the event dissemination so that we can analyze the behavior of these state machines under this event dissemination model and figure out exactly where these conflicts are that I showed in red on the previous slides. And then one could write code for an IDE, like a VS Code plugin for this stuff that tells you, oh, you need to handle some, handle or ignore some compensations here. That would, I think, make it a bit more safe for people to write this without having to learn everything up front. Yeah, I think that could be cool. So this brings me to my summary. The whole point was to make the devices autonomous, not only in data agency and ownership sense, but also in the communication and collaboration sense. So as soon as they are in the same network or have Bluetooth connection, they should be able to be more useful than a single device. So this poses challenges for the programming model. Classically, we just put things in a linear order, and that has a high cost. So this full autonomy weakens the consistency model, makes everything more interesting. You may need to compensate things, but my approach, so not everybody does this, but my approach to this is semantically meaningful events help you with many things. Most important, I mean design, but most importantly debugging and so on. So I want to keep that, and I want to keep generic state machines, but this poses some questions that have not yet been answered by papers from the 80s, unfortunately. So it's still ongoing work, and yeah, I think there's room for one more query language, but let's see about that. Thank you.
Okay, questions?
Hello, Roland. Thank you for the really nice presentation. I think you put it very clear, the problem, a problem which is complex. My question is, you mentioned about mobile devices and social network. This is something that interests me a lot. And my question is, this context involves many actors that are unknown to the central system, and maybe obviously you don't trust each of them. So how do you manage this model, or how would you this model that some actors show up eventually, they got disconnected, then not all them produce events that follow the rules, but either they are malintended or they are buggy, but they are like, there is a role for the server which is validating the events that are legal.
Yeah.
So how would you deal with that?
Okay, that's at least 3 questions.
Sorry.
So the last one first, because it's freshest in mind. The validation role played by today's servers in the cloud needs to move into the devices, obviously. And equally obviously, it wouldn't really help the developers, like all of you, to write correct code if you had to do all of that by hand. So this is why I'm trying to work with researchers of all kinds to figure out how to move this into the library or middleware or whatever have you on the local device to have the same basically security or safety. It's a mixture of both to ignore invalid inputs and so on that you would have on the server. Now, the reason why this is all a bit new and doesn't have many established solutions is precisely what the other thing that you asked about, so the dynamicity of the system. So if you have devices completely unknown and suddenly they show up, or suddenly they are no longer there, there are protocols that you can use. I mean, you can change the membership of Paxos But it's an involved process, and it has several weird cases that you need to handle. I would want this to be easier. But for some things, so it seems, for example, that history compression, so you don't want to have like a billion events to process before you can see your social network feed, right? So you would need to compress history, and that might need some form of consensus that you run from time to time. That isn't yet fully figured out yet. And the third aspect of the question, as I understood it, is so I'm interacting. So if it was just our phones, I don't know all of you personally, right? But I would also not want to trust a central authority because I don't know them either. I don't really know what Twitter does because I don't know the source code. So I would want to handle that just like we handle our relationships here by personal trust. So I trust your updates, and what the default is, I don't know yet, right? But if you're a bad actor and I see that you're trying to kill the system, I'll just say no. That identity is blocked because I don't trust you anymore. I would farm it out to the social network itself to regulate who is trusted and who is not trusted. I'm not sure whether it will work. So the reason why we started in factories is that this is a controlled environment. There's one owner, someone says, these are the devices, they set up a security perimeter, sometimes physical, always for the network, and so on. So there are no bad actors in that. And that, I mean, take one step at a time, right? First, we need to make it work. And I keep my feelers out for the security aspects to try and make sure that we're not building something that cannot be made secure. But this will take some time to figure that out.
This has been great. The one, I think you brought it up with the answer to his question. This system relies on a shared state model, so that the robots and the machines all understand what the state is and what it can transition to. I think you're saying that state machine is encoded in TypeScript in the machines themselves.
Currently, yes.
Okay, so that means that if you want to change it, they all have to update at the same time.
Right.
Okay. What came to mind when I was listening is there's a state machine language come out of Amazon step functions. A guy named Tim Bray produced it, and it's more of a declarative expression of what all the states are, what the transitions are, and the rules. Mm-hmm. So I think you could create a shared state model that you could probably sign or some way validate between the machines. Are we actually saying the same thing to each other to kind of get around or at least make it more robust? So.
Absolutely, yes. Yeah. I mean, that's this change would percolate basically through the fleet. In a factory, that's easy because someone controls it, as I said. So you would say, our production orders now have one more step because we figured out that we need quality control here because something was broken. And then you create this new model and you roll it out. Currently, what that would mean is you need to deploy a new Node.js app in the end. It's not yet moved into AQL because I'm not yet sure what the shape is. But eventually, I think these state machines should have a representation in this query language so that they are more compact. It's basically what you described. I have a language that describes the state machine that you can sign, for example, I don't know what content address. I mean, do you know the Unison language? It also comes to mind. Yeah, it's content addressed, so to speak. So you can let that disseminate and say, okay, run this state machine, run this on event function.
Sorry, you could declare the step functions, how the lambdas coordinate with each other. And then there would be a piece that actually moves data between and sets the state between them. But they could share that description. I'll look it up and send it to you because I think it would really. I mean, it'd be interesting to see how it would work to solve this one problem.
Yeah, thanks in advance.
Please give him a big applause.